The time has come to figure out how to find the area bounded by a polar curve. But before we jump into the formulas for that, let's refresh our memory as to how we do this in the world of rectangular functions. We should already remember that if we wanted to find the area between a rectangular function and the x-axis, then we're going to integrate that function with respect to x, and the bounds of integration are going to be from the left to the right of the bounded region, right? So from 1 to 4. Okay, so that's an expression that represents the area of region R. And then if we know what f of x is, then we can evaluate it. So let's not forget what's going on here. Of course, a equals 1 is the left endpoint. The smallest, let's call it the smallest x value. And we're going to say b equals 4 is the largest x value. Okay. The expression f of x changes, right? That's going to be this vertical distance, and then this vertical distance, and then this vertical distance, and then this vertical distance. It changes with x, right? F of x represents the height of each rectangle. So what does dx represent? Why are we multiplying f of x times dx? Well, dx is this little bitty distance right here, right? So these are f of x values, vertical distances. Then these tiny little horizontal distances, these are the width of the rectangles. dx is the width of each rectangle. Now, we don't use delta x, we use dx because we've calculused it. We've applied the limit, and the actual finite distance, the finitely large distance of dx gets infinitely small. It approaches 0. But we can't multiply by 0. We have an infinite number of zeros then, right? So that's indeterminate. So that's when the integral comes into play. So there's one more piece here, right? There's the 1, there's the 4, there's the f of x, the dx, and then there's also that integral symbol. And what does that represent? Well, the integral symbol is the sum of the areas, right? So that's what we're doing here. So it's important to recognize the pieces here so that we can maybe apply the same concept to a different sort of problem. For example, well, let's just refresh our memory here again with rectangular. The independent variable x moves from left to right, from 1 to 4. The dependent variable y, or f of x, measures the distance from the x-axis, right? We're measuring from the x-axis up to the top of each rectangle. And that's what we have, right? We're adding up the areas of a whole bunch of rectangles. Now, that's not what's going on in polar functions, because the independent variable theta doesn't move from left to right. As theta gets bigger and bigger, we're moving counterclockwise, anti-clockwise, around the pole, right? The origin. And then the dependent variable r doesn't measure from the x-axis, it measures from the pole, right? So we can think about the x-axis being wrapped up into a tiny little point right there in the center, and instead of moving from the left side to the right side, we're just spiraling around the pole. All right, cool. So that's fundamental difference in the way the variables behave in rectangular versus polar. So now if we take a look at a particular function, we're going to look at the spiral r equals a constant times theta. That constant happens to be 4 over pi. That might sound messy, but I'm just picking that because that is going to make our r values a lot simpler. We're going to use a similar concept with Riemann sums, but instead of using delta x values, we're going to use delta theta values, right? So if we were going to divide up this spiral from 0 to pi, we could let it be 4 subintervals, right? And if we want to pick equal subintervals, which we tend to like to do, then we're going to have delta theta equals pi minus 0 divided by 4, or pi over 4. All right, so that means that starting with the smallest value of theta equals 0, our next biggest theta value is pi over 4. And our next biggest theta value is pi over 4 plus pi over 4, or pi over 2. And then we're just going to keep on adding pi over 4 until we get all the way to theta equals pi. So we've got 1, 2, 3, 4 different changes in theta. And each one of those theta lines, right, theta equals 0, theta equals pi over 4, theta equals pi over 2. These are all values 3 pi over 4. These are all values that intersect our spiral at a point, right? At the pole and at r equals 1, and then at r equals 2, and then r equals 3, and then r equals 4. So just like we did with rectangular graphs, we're going to draw curves that have a constant output value. It used to be a constant output value of y. Those were the tippy tops of our little rectangles. Now our output is r. So if we draw a curve of a constant r value, these are going to be circles. So r value of 0, not going to go anywhere. R value of 1, we're going to keep on that r value of 1 until we get to here. And then r value of 2, we're going to stay on that r value of 2 until we get to here. And then r value of 3, and we're going to go all the way down to here. All right, yikes, let's try that again. If I draw it in the other direction, come on, you can do it. Control Z, I'm just waiting my computer to wake up. All right. All right. So the resulting 4 shapes can be used. Well, there's actually only 3 shapes because the first shape has an r value of 0. But the 0 area shape, and then this shape, and then this shape, and then finally this shape. These can be used to approximate the area bounded by the curve. Of course, the area that we would get here would be a little bit too small because I'm missing all of this stuff right here. And I'm missing all of this stuff right here, and I'm missing all of this stuff right here, and I'm missing all of this stuff right here. But at the very least, it will be a ballpark approximation. And of course, we can get better approximations simply by increasing the number n, right? N started out at 4, and if we make n bigger, that's going to be the number of sectors, right? That's what these areas or these regions are called, these little pie slices. This is a pie slice of radius 1. This is a pie slice of radius 2. This is a pie slice of radius 3. They're called sectors. So right now we have technically 4 sectors, but the first sector has radius 0. And if we increase that number 4 up to 8 or 16 or 1,000, then these little errors are going to be, there are going to be more of them, but they're going to be very, very small. But making n bigger is going to put a bigger number in this denominator. That's going to make delta theta be a very, very small value, right? And of course, we see where this is going, where it always goes in calculus, to infinity. So as n goes to infinity, delta theta approaches d theta, which is going to be the instantaneous change in theta. And that's when we're going to need our integral. Okay, so we're going to find a whole bunch of areas of tiny sectors, and then we're going to add them up from alpha to beta. We're going to use alpha and beta instead of a and b because they're representing bounds of theta. And theta is a Greek letter, so we're going to stick with Greek letters. You don't have to, but it's fun to draw alpha and beta. So just be careful here. The temptation is just to integrate from alpha to beta of r of theta d theta, just like we did f of x dx. That would be very bad because we're not adding up the areas of rectangles. We're adding up the areas of sectors. So what is the area of a sector after all? So if we have a circle whose radius is fixed and whose central angle is theta, and we needed to find the area of that sector, so the area of this region right here, well, we know that the area of the entire circle is pi r squared. The area of the sector is going to be a fraction of that. Well, what fraction? Well, theta is the part that we're interested out of the whole thing. The whole thing is 2 pi radians. Notice I'm not using 360 degrees. Calculus doesn't like degrees, calculus likes radians. All right, so that's the fraction of our area, or theta over 2 pi times pi r squared. So the pi's cancel out, and we have 1/2 r squared times theta. Okay, so that's the area of a sector whose radius is r and whose central angle is theta. Remember that the theta values keep on changing, though, right? So this is a change in theta from theta equals something to theta equals something else. So this is going to be our d theta value, and this is going to be our function. And notice that we're squaring it. And notice that we also have a 1/2 out front. These are all things that we tend to forget when we're not thinking about it. But in general, we've got this nice nifty formula. The area bounded by a polar curve is 1/2 the integral from alpha to beta of r squared d theta. And it comes from all the stuff that we were just talking about. All right. So in the next video, I'm going to go ahead and actually find the actual value of the area bounded by that spiral. But here's just an intro to the formula.